Welcome. We will discuss analysis of second order response surface. In last class, I have shown you that how to fit second order response surface given the experimental data. In this class, we will revisit this for 5 minutes and then I will straightway go to the analysis part, and it will take around 35 to 40 minutes of time, and the primary contents of this lecture is taken from the book written by Montgomery, Design Analysis of Experiments. So, you have seen this slide in last class also, that the second order response surface will be like this: y equal to beta 0 plus I equal to 1 to k beta I x I, then the second order term, then the interaction term, and error term will also be there. And you have seen that when the number of factors increases, the parameters also increases. Fine, these are the things what we have discussed earlier also. Now, question is that what are the issue that we should discuss when we talk about analysis of second order response surface. The second order response surface will be used to find out the optimum zone or settings for process operation or the system, at which where should we operate the system or the process, so that we will know that where is the location of the maximum yield or maximum response as such, or minimum impurity, that also minimum response, something like this. So, first one is that you have to know location of stationary point. Stationary point means the point where the first derivative is equal to 0. Okay. Suppose if we consider x1, x2 like xk, these are the factors which basically define the design space, then del x1 del y cap by del x1, del y cap by del x2. So, like this del y cap by del xk. So, these all, I think all will become 0 at the stationary point. Okay. So, then if x1, x2, xk, suppose these are the factors, but at the same time if we say that the point x1, x2, then xk, this is the point, because there are k dimensions and there will be one point where values are x1, x2, xk, let it be small x1, x2, xk. So, this is the point where the derivative, first derivative equal to 0, then this is a stationary point. So, you have to first find out the stationary point, and then what is the nature of stationary point, whether it is a point of minimum or point of maximum or point of or a saddle point where it is not sure point of maximum, it is not a point of maximum or minimum, it is saddle point. Okay. So, now let us see that how do we find out the point, that location of stationary point and the related computation. This part is known to you now, second order equation. When you estimate the beta, then we write these are all beta cap or beta hat. So, then the fitted value is y hat. So, y hat will be this portion except error term. So, this is what is y hat. Okay. So, now this one can be represented like this: beta 0 cap plus x transpose b plus x transpose capital B x, where small b is the estimate of the first order coefficients, the beta 1 cap, beta 2 cap, beta k cap, and capital B is basically it is basically it basically contains the second order that coefficient, that is quadratic part beta 1 1, beta 2 2, beta k k, and the interaction part like beta 1 2, beta 1 3, beta 1 k, and it will be 1 by 2, 1 by 2, and this side will be symmetry. So, okay. So, now if we consider that k equal to 2, suppose consider k equal to 2, then your b equal to beta 1 cap and beta 2 cap, and your capital B equal to beta 1 1, then beta half of beta 1 2, and then here again half of beta 1 2 and beta 2 2 cap, here all cap. Okay, so this is what is capital B. Now, so we can say that the point, the response surface is, our fitted response surface is y cap equal to this, and we say the location of stationary point is 1 where del y cap by del x is 0. So, del y cap by del x equal to 0. So, if you take derivative with respect to x, then beta 0 being the constant, its derivative will become 0, x transpose b derivative will be small b, and this quadratic term there will be 2 times b into x. So, we put equal to 0, and then you get the value of x, which is minus half b inverse b, and this x is nothing but the stationary point for x. Okay. So, 2 b x equal to minus b. So, x equal to minus half b inverse b, that is the point, stationary point. Okay. Then using this x's equal to this, you will be able to find out that the predicted response at the stationary point will be like this, that is beta 0 half of x transpose b. So, if you want to derive it from the basic equation, y s cap equal to beta 0 cap plus x transpose s beta plus x transpose s b into x, there I will write minus half b inverse b, because x x equal to minus half b inverse b. So, this we have seen. We have seen that at this equal to 0, x x equal to this. Now, in this formula we put x x equal to this value, and then you are getting like this. So, what is this? Then this is beta 0 cap x s transpose b minus half b, and b inverse will be I. So, this is nothing but x s transpose b again. So, then this one is beta 0 cap plus half of x s transpose b. So, this is the predicted value at stationary point. Now, we want to know whether this value is the optimum value or not. So, in order to do so, you do one thing, either you go for contour plot of the fitted surface or canonical analysis you do, because the stationary point can be a point of maximum, a point of minimum, or a saddle point. Determining whether the stationary point is a point of maximum, point of minimum, or saddle point. So, that is done through two methods, one is contour plot, another one is canonical analysis. So, let us see the contour plot. I have discussed contour plot several times earlier also, when we have fitted the factorial experiments and then found out the regression equation, and then the effect of x on the y through contour plot we have explained several times. Now, here you see this is what is our response surface. So, here there are two variables in coded terms, we have written x1 and x2 plus minus 1 to plus 1, minus 1 to plus 1, and this is your response variable. Now, if you see the contour plot, you see the contour plot mean here it is the contour plot mean all the point on this line will have the same y response value. So, that means here 96, then here 88, then 80. So, if you go along this direction or this direction, it is basically reducing. So, that means this is the direction of improvement, and somewhere here at the middle it will improve. So, this basically talks about, suppose this point which is somewhere here. So, this is point of maximum because of this shape. Now, here what happened, the shape says this is a valley, or in this case point of maximum saying it is a hill, here it is a valley, and you are getting point of minimum also. But the third one, if you see the contour plot, you go to one direction like this direction, then 100 and 116, here 100, then 84, 68, 52, here 84, 68, 52. So, it is basically it is difficult to tell that whether you are a point of maximum or point of minimum. So, it is a point which cannot be said either minimum or maximum. So, that is the saddle part. So, contour plot will help you, but you know that contour plot is possible graphically for 2 dimensional or at max 3 dimensional case when k equal to 3 or k equal to 2 or 3, but when k equal to more than 3, it is really difficult for all of us to use the contour plot. We require a better method of doing this work, and that better method is known as canonical analysis. What is the approach here in canonical analysis? You see, so this x1 and x2, suppose these are the contour plots. So, at the inner ellipse that talks about the response y equal to 80, then middle one 75 and the outer one is 70. So, somewhere here the maximum or maximum response lies. If you see the principal axis of the ellipses and the axis of x1 and x2, you see that they are not parallel. So, what in canonical analysis we want to do? We want to first shift the 0 point to the center of the ellipse, and then second we transform the x1 and x2 along the that principal axis of the ellipse. So, you want to access like this one is 1 and another one is another y w1 and w2, which are parallel to the principal axis of the ellipse, not that parallel to x1 and x2. So, you transform it. So, then what happened in the transformed dimension, your response predicted will become that response at the stationary point. Response means predicted response at the stationary point plus lambda 1 w1 square, lambda 2 w2 square, lambda k w k square. So, this is a special form which is a typical form which is known as canonical form. Okay. So, originally we are here x1 and x2, my new dimension is there w1 and w2. Why you are doing like this? Because your ellipse, the response contours, they are basically their principal axis are parallel to that w1 w2 or w1 w2, the 2 dimension parallel to the principal axis. We want that. So, here then you first find out what is the predicted value here, and then add the canonical part. So, your y cap will become ys cap plus lambda 1 w1 square, lambda 2 w2 square dot lambda k w k square, where lambda 1 lambda 2 dot lambda k, these are basically this is basically these are the eigenvalue of matrix capital B that you have already seen, and W1, W2, Wk are the eigenvector of matrix B. Okay. So, just seeing the lambda values, you are in a position to find out the. So, seeing the lambda value, you are in a position to find out this whether the stationary point is a point of minimum, point of maximum, or point of inflation, or that is the saddle point. So, let me repeat here that once you do this, so you are getting this, then lambda values also are there. Lambdas are basically eigenvalue of B, and W or omegas are eigenvector of B, and then seeing the value of lambda, you will note, you are in a position to tell whether the stationary point is point of maximum, point of minimum, or saddle point. If all lambda greater than equal to 0, then it is point of minimum. If all lambda less than equal, if all lambda greater than 0 and all lambda less than 0, this is point of maximum. And if some lambda greater than 0, other lambda less than 0, then this is saddle point. So, this is much it is better, it is a better model than the contour, because you can find out all the eigenvalues of B, and just by seeing the eigenvalues very objectively, you are in a position to tell whether you have gone to the maximum point or minimum point, or the it is not neither of the two. Okay. So, essentially what you require the matrix B, and that also we have seen earlier. So, with this background, let us see the example. This example we have discussed in several classes. Now, in last class I have shown that the CCD is used here, and we have also got this one, the second order response surface, this one. What is our second order response surface? For the example y, which is basically yield, is 79.94 plus 0.995 x1 plus 0.515 x2 minus 1.376 x1 square minus 1.001 x2 square plus 0.25 x1 x2. Okay. So, then what is this? Beta 0 is 79.94, then B is your 0.995 and 0.515, and capital B is what? That beta 11 cap, beta 22 cap, half of beta 12 cap, and half of beta 12 cap here. So, this will be, what is beta 11 here? Beta 11 means minus 1.376. What is beta 22? Beta 22 is minus 1.001. What is beta 12? Beta 12 0.25. So, this is 0.25, but please remember there is half. So, off diagonal element with half. So, this by 2 and this by 2. Another means B matrix will be minus 1.376, 0.125, 0.125, minus 1.001, 2 cross 2. So, let us now analyze this response surface using the methods that is known as canonical analysis. So, first one you see the contour plot, then I will show you the. So, if you see the contour plot, you are getting like this, and here is the point, that is the point, stationary point, and if you just project across this axis, that is time, and this axis temperature, you are finding out the value for that time is around 87 and value for the temperature is around 176.5, and at this point what is the value of station yield is 80.21. And now, okay, from this plot you are finding out this is a point of maximum, because you see that the response surface is a hill like structure. Now, we want to use the canonical part. So, what is the stationary point? Xs is minus half B inverse B. Now, B part is given to you. So, B part is small b is this, and this one is this. So, what you require to do? You require to find out B inverse. Okay. So, B inverse into, so what do you want? Half B inverse B, that is minus half, that is your Xs, minus half B inverse B is Xx. So, this value when you compute, it will become 0.389 and 0.306. So, B is this, capital B is this, you find out the inverse of it, multiply, divide by half, minus symbol you use, and then you will be getting this one. So, that means this is the point X, this is the stationary point in terms of design variables. Then what you want? You want Ys, this value. So, what is the Ys value we have computed earlier? Ys value we have computed that Ys, that is predicted Y at S is beta 0 plus half x inverse B. All those things are known to us. So, if you apply this one, then beta 0 is 79.94 plus half your stationary point, its transpose 0.8389, 0.306, and into B. What is your B? 0.995 and 0.515. Okay. So, this value is 80 point, how much it is? 80.21. So, you are getting one end, what is the stationary point, what is the predicted response at stationary point. Fine. Now, what you want, whether this stationary point is a maximum point of maximum, because the contour chart says this is point of maximum. So, in order to do so, what you require? You require to find out B minus lambda I determinant equal to 0 to get the eigenvalue and eigenvector, and your B is minus 1.376, 0.125, 0.125, minus 1.001, this minus lambda 1001. So, this is what is B minus lambda I equal to minus 1.376 minus lambda 0.125, 0.125 minus 1.001 minus lambda. So, this is my matrix. Okay. So, now you take the determinant, then the determinant of this, this will give you the equation called lambda square plus 2.3788 lambda plus 1.3639, this put equal to 0, this you put to 0, and then find out the roots, of this equation lambda 1 and lambda 2. So, lambda 1 minus 0.9634 and this one is 1.4141. Okay. So, now you know you have lambda 1. So, now all the lambda 1 lambda values are negative. So, this is a point of maximum. Once you know the lambda values, you know whether point of maximum or minimum is reached or it is a saddle point. Okay. Now, come back to this. So, because both lambda 1 and lambda 2 are negative and the stationary point is within the region of exploration, we conclude that the stationary point is a maximum canonical form of the fitted model. Okay. Now, here we have shown that how beta 0 is calculated, that is the average value at the center point. Fine. Now what happened when we could not operate the process at the stationary point? Okay. So, many a times we could not operate the process at stationary point because this combination of factors may result in excessive cost. We require to move from the stationary point to a point of lesser cost without incurring large losses in response. The canonical form of the model indicates the direction of less sensitive to loss. Exploration of the canonical forms requires converting points in the W1, W2 space to the point in the X1 and X2 space. What is happening here? Let us see. So, you have seen that. So, our stationary point is this, and then this one is W1 and this is the W2 axis, and suppose your response surface, your contour plots are like this. Suppose you cannot operate here because maybe cost is prohibitive or the technicality is a problem for operator's point of view or something like this. So, then what happened? You want another point, another location, another zone where you will operate the process. You will not incur much loss. At the same time, it will become convenient to do it. So, that is possible because you know that the directions x, y1, w1 and w2, and you know that which direction, if you go to the direction, what is the loss, minimum loss will be in which direction, that also known to you because you know the function, you know the y cap in terms of ys stationary point plus lambda 1 w1 square plus lambda 2 w2 square. Either go along this direction or this direction, or depends on the value of lambda, which direction you will incur less loss. So, this is one advantage of having this. Now, second is that okay, suppose you will go along W1 because lambda 1 is giving you a better situation. Then question is that you know those in W1 and W2 dimension, but you have to experiment it. So, you have to convert back to x1 and x2. So, W1 and x1, so W1 and W2, this dimension it should be, there must be relation with x1 and x2 dimension. This how do you know? So, there is the concept called, this W is related with x with this equation, W equal to m transpose x minus x s, where m is basically a orthogonal matrix and it is k cross k dimensions because we have k number of factors. Then this ultimately leads to this b minus lambda I equal to 0. Now, you already know the lambda values, put one lambda and then find out the m value, put another lambda, find out the m value, and then what happened, once you know this m, that means m transpose is known. Now, using these equations you will get the relations between x and omega. This is what we are doing here. We know B, we know lambda. Now, you put the first one, what is the, so minus this into this value. So, minus is there, minus plus minus is minus is plus. So, your resultant matrix is this, and it is multiplied with M11 and M21 because here is the 2-dimensional case. Then you are getting these two equations. Now, these two equations once you and two unknowns, so you can solve it, but you will get a situation where you find out that you will get infinite number of solution, unique solution you will not get here, and as a result you require to normalize it. The normalization one is this, j equal to 1 to k m I j I square equal to 1. So, that is what we have done, m11 square plus m21 square, this square root is this value, and then using this 3, this one and this 3, you are finding out m1 and m2. So, from these two you are getting the relation between m1 and m11, m21, that relation you are getting. Now, using this one, this normalization, you are able to uniquely estimate the value of m11 and m21. This is very simple one, just you do one thing, you write down in terms of relation m11 equal to in terms of m21 from the first equation, and from the second equation you will get the similar thing. So, unique, that is infinite number of solution to unique solution because of this normalization. So, now m11 m21 is known. So, with reference to lambda 1 it is known. Now, with reference to lambda 2 second eigen value, again find out the eigen, that m11 and m21. So, then you will ultimately found out the m is 0 point this value you see m11 2898 9.9571. So, 2898.9571, and this is from coming from the lambda 2. Now, W1 W2 equal to m transpose x minus xs, this you are getting, and putting this you are getting this equation. Okay. So, putting this you are getting W1 and W2. So, fine. If you have W1 value and W2 value, you will get x1 and x2. Once you get x1 and x2, you can convert to the original variable values, and then you experiment there. Okay. So, this is what is the analysis part. So, response surface methodology, I just conclude that we have given you the approach, the purpose, then we have shown you that that is method of steepest ascent or descent, then first order model, regression model, then second order regression model, how to compute all those things. We have discussed response surface designs, then we have shown you that when you how to analyze the second order response surface, and then when you are not in a position to operate the process in the point of maximum, minimum or the stationary point, how to go to the next point of operation without incurring much losses. We have given you two kinds of analysis, contour plot based analysis and canonical analysis. So, all those are very, very important, and I hope that you will be able to answer the questions that will be posted in the exam, and we will show you some of the Minitab based computation in next few lectures. Thank you very much.